what's waiting in the future. So first, atomic force microscopy, or AFM, very briefly. You've got some very sharp tip attached to some cantilever, and then this tip, when you're imaging some sample, it's in some force interaction with the sample, so that you could say that the tip is kind of touching the sample. And using this kind of fairly simple idea, it's possible to get images of sample at extremely high resolutions. So this is one of the like pioneering experiments in the like very high resolution AFM from a bit over a decade ago, where they imaged a benzene molecule using AFM, and in the resulting image you can really see the sample at resolution that is going to, like, you can see like individual connections between atoms in the sample. So this is just a single molecule sitting on a surface. And there's a lot of other great stuff, like imaging some organic or biological molecules, and like characterizing some reaction processes on surfaces, and some like really exciting stuff can be done with AFM. But of course, not all is perfect in the world. So mostly the AFM imaging is now limited to these fairly flat sample geometries. So for example, if we have like this bromodichlorobenzene molecule here, in these kind of cases, it's fairly easy to map the contrast in the seen in the image to the geometry of the sample. But then if you go to something more complicated, like the 1s camphor molecule here, then it's much harder to know like what you're actually looking at when you're just seeing the AFM image. So we're hoping that we could tackle this like interpretation problem using machine learning. And I hardly need to tell you the impact that machine learning has had on the sciences and society in general. And really at the center of all of this are these neural networks and the so-called deep learning. And just like picking out a couple of examples, what you can do with this stuff is like computer vision tasks, like image classification or image segmentation or generating images. And one of the like famous examples is that sort of artificial intelligence is that the best AI is now already beating the best human players in, for example, in the Go board game, and other these kind of decision processes can be done using deep learning. Also, all sorts of natural language processing tasks like machine translation or generating text. And from the end of last year, there was this really hyped model from Google's DeepMind team where they introduced this so-called AlphaFold, what they called AlphaFold model, which is like deemed to have solved the protein folding problem in biology. So this is like really big stuff. And like what we're trying to do with machine learning is hopefully recover the geometry of the sample from the images, even in these like more complicated examples, and other information that we want to retrieve is like this chemical information, like the electrostatics or the like elements of the atoms. So for example, even in this case, even though the geometry is kind of easy to read, it's not so easy to know like which one here is bromine, which one is chlorine. And of course, if you can automate the process, make it faster, easier, then that's good. Looking at AFM in a bit more detail now. So again, you have this very sharp tip, which is in some kind of interaction with the sample. Here we will be considering the frequency modulation AFM, where the idea is that the tip is oscillating at some constant amplitude. And then the thing that you actually measure is the change in the oscillation frequency of the tip. So the wiggly line here is kind of signifying that you have one oscillation frequency where there's nothing in the sample interesting in the sample, and then when there's some kind of bump, then you might get a different oscillation frequency. And then if you scan over your sample, then you can get this contrast map of what is in your sample. And if you go at different distances, then you get different kind of contrast in the image. And one of the important kind of tricks in the very high resolution AFM imaging is this idea of functionalizing the tip by attaching some additional particle to the end of the tip. And common one to use is, for example, the CO molecule. And the idea here is that this additional particle at the end of the tip is flexible so that it can kind of bend around the sample when you're approaching, so that it doesn't disturb the sample too much. And it's also chemically inert, so that it doesn't chemically react with the sample. With the bare metal tip, it's often a problem that when you go close to the sample, then it's easy to disturb the sample, and the sample might, if it's delicate, it might, for example, jump onto the tip. So this is really important, this functionalization. Now, from the machine learning perspective, AFM, there's kind of problem that AFM is not really a very high throughput method, so it's difficult to get very large data sets of images, which is often required for the machine learning. So what we do instead is that we do simulations of AFM images using this so-called pro-particle model, which was introduced by Happel and others in 2014. Without going into too much details, the idea in the model is that you're considering this pro-particle, which is attached to a simulated AFM tip, where the pro-particle is standing in for the flexible particle at the end of the tip. And it's then in a force interaction with the tip and the sample using some classical force fields. The kind of important points here is that it's fairly accurate. So yeah, for example, we can compare the simulation of this benzene molecule experiment measurement compared to the actual experimental image. We can see that it's pretty close, actually. And number two, it's very efficient, so or very fast. So we can do like on the order of 50 simulations per second, so that we can generate this large data set of samples that we require for the machine learning. Now for machine learning, what is actually machine learning? So, well, there are many definitions, but in general, we are considering a case where we can write some program that could learn a task without explicitly telling it like what the task is. So if we think like traditional programming, that we are kind of thinking in this kind of algorithmic terms, that we get some data and then we hard code some set of steps that should be done on the data in order to get the desired output. But in many tasks, it gets just like really difficult to make these kind of simple algorithms. So in these cases, we can resort to machine learning, where the idea is that you instead give some examples of the task, and then the program should learn the task by itself. And usually we consider machine learning programs to be a kind of artificial intelligence. In practice, what we do is function fitting. And there are many different types of machine learning, but considering the like most often used supervised learning, the procedure is roughly that you first gather some database of examples or some input-output pairs. which exemplify the task that you're trying to perform. Then you propose some kind of function, a model, which has some parameters, so that when you tune the parameters, then the model will give a different output for a given input. And then you fit the parameters of the model to the database of examples that you have, so that the model gives the correct answer as often as possible. This kind of simplified version of what is done. In practice, there are a lot of complications, like gathering the database may not be so simple. For example, in our case, we had to do simulations. Proposing a function, like there's a lot of different functions that you could choose from. And then feeding the parameters is not very easy either. And even the whole idea of what is a correct answer is not always obvious. So even though we kind of say that the program is like learning a task, like in practice, there's a lot of fiddling that the engineer has to do in order to make the model work. Now, the specific type of model that we are considering here is the artificial neural network, which is a model that is inspired the biological neural network, like the brain that all animals have. So the structure of the model is such that you have a whole bunch of these layers, where at each layer you have these so-called neurons, which are connected to the neurons in the preceding or the next layer. And so each layer here is some vector of data, which is then transformed into another vector of data. And the way that this happens is that you take your input vector of data and then you multiply it by some matrix, which is parameterized, or is like the entries in the matrix are the parameters of your model. And then you also add some vector, which also are the parameters of the model. So in like summary, you do a linear transformation to your vector, and then you put it into this function G, which can be any nonlinear function. This is often called the activation function of the layer. And then on the other side comes out another vector. And then our artificial neural network is simply a whole bunch of these layers stacked on top of one another. So you do a whole bunch of these transformations of the data that you have, and then at the other side comes out the answer. So how big should your matrix and this additional vector be? Well, that's a so-called hyperparameter, which means that you get to choose for yourself. And how do you choose? You just try a whole bunch of different things. So there's some like rules of thumb, like of how many parameters your network should have, but there's no like hard-cast rules. And then the activation functions. Without going into too much detail, the two that we use here are the ReLU and the leaky ReLU functions, which are actually piecewise linear. So if the input is positive, then the output is the same as the input, so it's just a linear function. And then for the ReLU, if the input is negative, then it's just a flat zero. And for the leaky ReLU, you let in some small contribution of the input. Then feeding the parameters. So what you first need is a loss function, which is measuring for a given example how good is the prediction of your model. An often used loss function is the mean squared error. So if we consider that y is the prediction from the model and the y tilde is the reference that you labeled yourself, then the loss is for each element in the output, you take the difference between the prediction and the reference, you square that, and then you take the average over all the elements. So it's easy to see that if the prediction is exactly the same as the reference, then this loss is 0. And if it's anything different from the reference, then it's something bigger than 0. So what you want to do then, of course, is to minimize this loss function, make it as close to zero as possible. And the most often used way to do is gradient descent. The idea here is that if you take some parameter w in your model, then for that parameter you take the gradient of the loss function with respect to the parameter, and then you change that parameter by stepping in the opposite direction of the gradient. So the idea here is that you're kind of stepping downhill to the minimum of the loss function in iterative steps. In neural networks, there's a specific algorithm called backpropagation or backprop, which does this very efficiently. The name comes from the fact that because the neural network is a function composition, then you do the gradient calculation by using the chain rule of derivative, starting from the end of the network and then kind of going backwards towards the beginning. Now that you're feeding the parameters in your model, one thing that you have to wrestle with often is overfitting. So if we, for example, take this some data here represented by the blue crosses, and then we fit some function, which is the orange line, to the data, then we might find that for the examples that we have, the fit is actually pretty good. So that it's like finding the average case quite well. But then if you step outside the range of training data that you have, then the fit actually becomes really awful. So the true function here would be, for example, this quadratic function represented by the red line. So in this case, the model was overfitted. And in this case, it was caused because the model function had too many parameters. So if you had chosen a better number of parameters, then you might have gotten a fit that generalizes better to examples also outside your training set. In this simple case, it's easy to see that the model is overfitted, but if your model output is the model is very complicated, then it's not so easy to see. So the way that often you monitor for overfitting is that you split your data sets into these training, validation, and test sets, where the idea is that the training set is only used to fit the parameters, and validation set is used to then fit the hyperparameters, so that you try a whole bunch of different versions of your model and then pick the best one based on the validation set. And then finally, the test set, you don't fit any parameters to it. It's just the final test of how good your model actually performs. For neural networks in particular, there's this thing called dropout that is often used to reduce overfitting. The idea is very simple, that if you take some layer in your network, then you just, during training, randomly take out some of the neurons in the layer, so that it becomes just 0 according to some predefined probability. Then going into convolutional neural networks, which is a kind of variant on the neural network architecture. In many cases, the data that you have has some kind of spatial regularity. For example, in images, the pixels are arranged in some regular grid. And you can take advantage of this regularity in your data. So what a CNN does, if we take some particular layer in that model, so if your input, for example, is some kind of image where you have a whole bunch of pixels, each one and each pixel has some value attached to it, then you transform this image into another image by convolving it with a filter. So what that means is that you have your filter which also has some numbers attached to it, and then at each position in your input image, you take some local neighborhood of pixels, so that you multiply the filter values with the input pixel values, and then you take the sum, and then you store that sum in the pixel of the output image. And then if you scan all over the whole input image, then at the output you get also a different transformed image. This might seem quite different from the artificial neural network that I showed before, but actually it's kind of the same, except that the connections only exist like between some locally close neighbors in the subsequent layers. Another important building block in the CNN model is the so-called pooling layer, where the idea is that you kind of summarize the information that you have in your features in your image. So the way that you do it is that you again then take some local neighborhood of pixels that you have, and then you perform some operation that only outputs a single value for that neighborhood of pixels. Common operations to use are the average pooling, where you just take the average of the pixel values, or max pooling, where you take the maximum of the values. So this is a way of sort of compressing the information as you go forward in your network. Now getting back to the AFM images, our problem at hand. The question that still remains is that what should the model output? Like, what is the information that we want to extract from the AFM images? First thing that you might think of is that, okay, well, we want to know where the atoms are, so maybe we just take list of coordinates for each atom in the molecule. But in practice, this turns out to be not so ideal. The problem is that there are some certain invariances inherent to the structure of the molecule that the network has difficult time learning. So, for example, if we translate the molecule to some other position, it's still the same molecule, but the coordinates of the atoms change a lot. So it might be very difficult for the model to learn this kind of correlations. And another problem is that every molecule could have each different number of atoms in it, so that you would have a target of varying size, which is also difficult. So this is not a good way to go, or not an easy way, at least. So what we have done instead is design this so-called image descriptors, so that we generate some kind of image that encodes the information that we want to learn from the input AFM image. And this works nicely for the convolutional neural networks, because then the input is an image and then the output is also an image. So there's a few different descriptors that we have designed. The first one is the van der Waals spheres descriptor, where each atom is represented by a sphere, and then this is projected onto a two-dimensional image where the brightness tells you how close that atom is. So it gives kind of idea of the geometry of the sample in a sort of easily identifiable way. The atomic disks, each atom is represented by a small disk, and again, the brightness indicates how close the atom is. So it's a very similar idea as with the van der Waals spheres, but it's like more precise in pinpointing the exact locations of the atoms. The third is the height map, which is an isosurface of the force field between the sample and the tip. So it sort of summarizes many of the interactions between the different atoms in the sample and the tip. And this is especially we use this in relation to the last descriptor, which is the electrostatic map, which is the vertical component of the electric field of the molecule calculated on the surface defined by the height map. So that the idea is that if we combine these two, then it gives sort of a three-dimensional map of how the charge is distributed over the molecule, so that the blue regions would correspond to high electron density and the red regions to electron depletion. Then going into the specific model architectures that we use. So we use convolutional neural networks. And these are fully convolutional, so all the layers have this kind of image structure. We use two models. The first one, we adopt the DSH model because it predicts the disks and the spheres and the height map descriptors. And the input to the model is a set of AFM images taken of the sample at different tip sample distances. So the way that the data is transformed in the network is that we have these convolutional layers and average pooling layers, so that in some sense the information in the AFM image is gradually encoded into a smaller and smaller size of an image, and then this more abstract representation of the information and is then sort of decoded into the three different descriptors that we use, and the decoding works such that there's like three stages where at each stage we upsample the image back into a bigger size, and there's some more convolution layers in between, so that finally at the end comes out the descriptor that we want to predict. That was the first model, and the second model is the one that we call the electrostatic or the ES model, which predicts the electrostatic map and the height map. So the task is roughly to predict the electrostatic properties of the sample. The input to the model is a bit different than in the first case. Here we actually have two different inputs to the model. Two different sets of AFM images, where each set has been imaged using a different functionalization of the AFM tip. So if you recall, we have this, for example, this CO molecule at the end of the tip. So here we have one AFM set imaged with a CO tip, another one with a xenon tip, and I will explain in a minute why we do it this way. The overall structure of the network is quite similar, that you have this kind of encoder part where the image size is gradually reduced, and then the decoder which pulls it back to the original size. The biggest difference is this so-called unit connections, which come from this very popular variant of the fully convolutional neural network. The idea here is that you put these skip connections into the network so that earlier parts of the network have a direct connection close to the output of the network, where the idea is sort of that when you do this downsampling, then you gradually lose some of the finer details. So then the skip connections could put those details back into the prediction. And why do we use two tips in this case? It turns out if you put a different functionalization of the tip, then you actually get a very different image of the same sample. And this paper in particular noted that a major part of the contribution of why these images are so different is the electronic charge associated with the different functionalizations of the tip. And in this paper, they also show that if you map the different distortions in the image, you can actually extract the electrostatic potential and field of the sample from the images. So we're trying to do something quite similar using the machine learning approach, which is more automated. Then finally going into the results. So first for the geometry prediction, and this is for the simulations, and a couple of examples here. So here at the top, we have the AFM image, which is given as the input to the model. And then there's the original molecule geometry. And then we have the prediction and the reference for the three descriptors, the atomic disks, the vanilla spheres, and the height map. And if we compare the prediction to the reference, then at all of the descriptors, we find that the overall the prediction is very accurate, so that we get the correct contrast, and where we can like identify the overall geometry of the sample that we are looking at. Some of the difficulties that the model has is that the prediction tends to be a bit more blurry in such way that it's not so easy to distinguish between the individual atoms in the predictions. And also some of the deeper atoms in the reference are not often not found in the prediction. And here's another example which kind of shows how this approach could be useful. So here we have this kind of carbon ring structure molecule, which is fairly flat, but it's tilted a bit in a way so that the AFM images are actually really difficult to decipher. But then the prediction of the network shows the overall structure of the geometry of the molecule in quite clear way. So this kind of cases we could like maybe directly read the geometry in an easier way using the predictions. Now, of course, then the real test is on the real experimental data, because I remind you, we trained the model on the simulations. So we obtained a whole bunch of experimental images of this 1s camphor molecule. So in this image, each row corresponds to one experiment, and on the left side we have the experimental AFM images. Then we take these images and then we produce, we put them to the machine learning model, and then we get the output descriptor. In this case, we show the one was spheres descriptor. Now, of course, we have the problem that we don't know what is the reference answer that we should compare against. So what we did instead, because in this case we knew what the geometry of the molecule was, is that we took a whole bunch of different configurations of this molecule, looked at that from all different sides where we could compute the corresponding descriptor, and then we compared the simulated descriptors via cross-correlation to the predicted descriptors from the experiment, and found some list of matches for each experiment. And then we can, of course, also do the AFM simulations using the geometry that we know, so that we can overall see that the descriptors match quite well in each case, and also the simulation is not too far off from the experimental AFM images. So this shows that at least the machine learning model is also giving something quite reasonable even for experimental images, even though it wasn't trained on experimental data. And these results we already published in Science Advances last year. So you can also go read that for more details. This part is not yet published. So for the electrostatic prediction, again, starting with the simulations, we have 3 example cases. And again, here the input now is 2 sets of AFM images, one image with the CO tip and the other with the xenon tip, where you can see that we get quite different contrast of the same sample using the 2 different tips. And then on the right side, we have the prediction and the reference for each case, and we find that the predictions are quite good in every case. And in this case, the height map is shown as this contour map in order to put into the same image. For the last case, we can also compare to this paper where they did Kelvin probe force microscopy experiment of the same molecule. So Kelvin probe force microscopy is another way that you can get measure the electrostatic properties of the sample, and we find that we find a very similar looking pattern in their experiment compared to our simulation. So it seems that our simulations and the machine learning predictions make sense. And of course, again, the experiment is the real test. We have a couple of example experiments that we have performed where we have obtained both the CO and the xenon tip measurement. First one is the bromodichlorobenzene molecule, which is shown in this part. And comparing simulation prediction to the experimental prediction, we see a very similar pattern where the overall over the halogen atoms, the chlorines and the bromines, there's a negative charge. And then in between over the hydrogens, we see this positive charge both in the simulation and the experiment. In the experiment, the positive regions are a bit weaker, but overall it's a very good match. Not just qualitatively, but also quantitatively, the numbers that we get out are very similar between the simulation and the experiment. So this is very good. And the second example is this PTCDA molecule. Again, comparing the simulation to the prediction, the experimental prediction in this case is a bit more noisy, but the overall pattern is very similar, so that we have this negative charge over the oxygens in the molecule, and then positive charge in sort of the middle part of the molecule. Quantitatively, it's not quite as good as much as in the first case. The negative charge or the oxygens is a bit weaker in the experimental predictions, but it's still roughly up within a factor of about 2. So it's not too far off. There's some additional features seen also in the experimental predictions, which probably should not be there. So the robustness of the model probably still could be improved quite a bit. But like overall, we find that the matches are fairly good at this point already. So in conclusion, we have introduced this machine learning based approach for predicting the sample geometry and the electrostatic properties from from AFM images. Overall, we find very good performance on the simulation predictions, and on the experimental predictions, it's also quite good. But there's some issues that could still be improved. And of course, the difference between the experiment and the simulation predictions is that the model is trained on the simulation, and the simulation is not exactly representative of reality. So there's some issues there that if we could improve the simulations or do the simulation a bit different way so that we could match the experimental situation better, then this could be we could improve the model predictions quite a lot still. Looking at the future directions, we in this case we considered fairly simple molecules, and we would in the future want to proceed towards more complicated geometries and cases where we don't exactly know what we're looking at even from the start. So we have obtained this some AFM experimental AFM data for this silotetraose molecule, which has a lot more complicated structure, so that it's going to be much more difficult to know or like a lot more difficult to decipher what we're actually looking at. So this is really interesting going forward. And then lastly, well, we also been looking at some different types of machine learning models that we could use, specifically these graph neural networks, where we have been developing this model where the idea is that we take the AFM image set and then we could iteratively produce a graph corresponding to the geometry of the molecule that we see in the image, so that at each step we add some atom and some bonds to the graph, and then finally the models at some point decides that okay, this is now complete. So that could be another way to do this geometry prediction. And this now concludes the presentation. Thank you for your attention.
Okay, thank you, Nico, for the presentation and for staying in time. So now the midterm is open for general questions from the audience. I mean, Daniel, you can already ask questions if you want, but first, anybody from the audience is free to ask. Actually, I could start with a question which I had on the electrostatic part that you showed. So the electrostatic surfaces that you predict, it's really impressive, and also the Agrima experiment. But I was wondering about the sort of the motivation behind it, what it actually is that you want to know with machine learning, or you want to find out with machine learning. So in your first example, it was clear, right? In the experiment, AFM experiment, you don't know where the atoms are. And then through your model, you find out what the sort of atomistic structure is of what has been imaged. Yeah. But for the electrostatic surfaces, both can be measured experimentally, right? So you're predicting something that can already be measured experimentally. So what's the gain then?
Yeah. The experimental prediction of these electrostatic fields to actually like quantitative accuracy is still quite difficult. For example, with the KPFM, there's some like pre-factor to the measurement which is unknown, which makes it very difficult to actually give out a number that would tell you exactly what is the field at that part. And even in these cases, like in this paper, they like already got some answer out. But if you could like do it with machine learning without like manually going and looking at these things, then the automation thing is of course already also there.
Okay, so it's meant to be a tool that would replace, for like an AFM lab, that would replace the Kelvin probe measurements. If you have the AFM measurements, you can just straight away predict what the electrostatics are without having to do Kelvin probe. Okay.
Possibly in some cases. Well, I imagine there could be cases where doing the two-tip measurement could be, for example, more difficult than KPFM, but it's
That too, yeah.
but it's at least some alternative approach, if not always the easiest approach to use.
Other questions from the audience?
I have a few, but I mean I can wait if somebody else has a
Yeah.
question.
Well, you get your turn. Then let me ask another question, and then maybe I can hand over to Daniel. So if you go to your network architecture, the one that you used, yeah, this one, yeah. I wasn't quite sure why you had convolutions also in the upscaling. So it's clear why you upscale from in the decoder, right? So you need to get back to a larger image again. But why are you adding these convolution layers, and what are they actually convolving over?
You mean like in this part?
The blue ones there, yeah, exactly.
Well, in this part of the model, the feature maps are maybe not exactly the thing that you yet want to get like in the output. So you would still need to somehow transform whatever you have there. And also the upsampling is done by nearest neighbor upsampling, which is not a very like intelligent way of doing upsampling, but it's very fast. So the convolutions then can smooth out the differences and pick out the like interesting features, or at least that's my like intuition. But of course, it's kind of black boxing.
But are there convolutions now? Because you have 64 feature maps, right? And that are in the first step, that are of 32 times 32 dimensions. And then you're bringing this down. So are the convolutions basically picking points from every filter and reducing, say, 2 filters to 1, that you get fewer and fewer? Or is that the upsampling? It's just because normally the convolutions, they produce more images than you had before, right? You can see how the number of channels goes up when you go from left to right. And then now if you applied the same, you would get even more than you had before, but somehow you get less.
Oh, well, that's decided by how many filters you put into your convolutional layer. So that's also like a hyperparameter, how many filters you choose to use at this layer of the model. And usually it is the case that the deeper that you go into the model, the more channels you use. And this is like in the image classification task, that probably makes sense because you're really reducing the size of the feature map down to just like a linear vector at the end. But here we are going back up into the big size. So if you used a very large amount of channels also at the end, then it would make the network really heavy to compute.
Yeah, I don't know. I still don't fully understand how the convolutions work on the right side of the network, but maybe we can look at this in more detail some other time. Okay. Any questions from the floor? Anyone from the audience? I see we have experts there. Okay, if that's not the case, then I hand over to Daniel.
Thanks. Yeah, first of all, thanks for the presentation. It was really clear to me. I have a few questions. I don't know if I have like a time limit or something, but please just cut me off if I I start talking for too long.
Yes, there's no strict time limit, but
Okay,
don't
I'll try
push
to keep it.
push it.
Yeah, exactly. So yeah, first a really quick question. It's just related to the question by Patrick, which is why did you end up using this particular model for ES and the other one for the DSH? I think it was. I mean, there are tons of architectures that you can use. Why choose specifically these ones, and why are they different between the two?
Time difference. Maybe this model came first. I was like just getting into the whole machine learning thing and learning about these convolutional neural networks. I didn't know about this unit, for example, yet. So I was kind of trying to find something that works, and this is the first thing that worked quite well. And then
But then doesn't that work also for the ES model? Or did it not work?
It worked to some degree, but when we, for example, added this unit connections, skip connections, then we found that the model worked quite a bit better. So it's like a process of gradual improvement that led to the different model in the end.
Yeah. It's just mostly, let's say, trial and error kind of.
Yeah.
Based. Yeah. Okay. Yeah. Then to a lot more bigger question. So one thing I am missing also here from the presentation, but also I think in the report is what you used as training data. What did you train on? What kind of images were they, and from what molecules? And this just more of a generic comment is, especially for these machine learning based methods. To me, at least, it is becoming more and more important to also state these very clearly and correctly, because it kind of, with all this machine learning stuff, the training data kind of becomes part of your method as well. Because if you train on different data, your kind of your algorithm changes. So yeah, it becomes important to also describe the data. Well, you describe your method, also describe the data very well.
Yes. So the data comes from our simulations. The molecules which we use for the simulations are one of our colleagues in the group does this using density functional theory and coupled cluster based methods to like optimize these geometries, and we have like thousands of these molecules that we use to generate the simulated images. So I think the training set was about 5,000 molecules, and then we take 30 different rotations for each molecule, so that we get like 150,000 about training samples.
So are you worried about maybe the possibility of, let's say, some kind of atomic configurations not being present in the training data that might be present in just real data that you then completely miss? I mean, maybe the network then becomes very confident, like it's this structure, while it's not giving it because it was not in the training data.
Yeah,
or are there ways of?
And this is something that we have resolved with along the way. So in our training set, most of our molecules are this like fairly three-dimensional examples. Like, for example, this one is camphor, so something that looks kind of like this. And then when we trained our model on these kind of samples, then we found that actually it often doesn't do quite as well on these like more flat things where you see a lot of atoms in the same plane, which is kind of ironic, like considering that this is usually like the easy case. But then we have also like made sure that we also have this kind of more flat examples in the training set. And there's of course like what elements of atoms your molecules have, and we have some subset of like 10 different elements, and probably we shouldn't expect the model to work quite well if we take some molecule which has some atom with an element that we didn't have in the training set.
I guess I'm not sure how, so I'm not an expert at all AFM stuff, but I guess usually you have some kind of idea of what you are scanning, I guess, right? It's not completely
yeah, well,
random, yeah. So then it's not really a problem because you can just, let's say, choose your training data such that it fits with what you expect to find, I guess.
yeah, at least to some extent, or the experimentalists usually want to know what is in their experimental setup. There are some substances that could like destroy your machine or make it not work so well. So you yeah, often you have at least some idea of what you have in there.
Yeah. Okay, then I guess time a final question, which is related to the well, these kind of experiments with the real data. Can you go up a little bit just to the slide above? Yeah, that one, the geometry prediction. So to me, it's a little bit unclear here. What you're exactly testing here? So what can you conclude from these experiments? Because if I understand correctly, you take the experimental data, you run it through your network, and then you match the disk output, no, sorry, the sphere output to something from your set of simulations, right?
Yeah. So
So what can you then conclude that you find something matching?
yeah, well, the sort of long-term goal would be that you just give the AFM image and then it gives you like the exact answer of what you're looking at. But in this case, we took a simpler approach where we know what is the molecule. We just don't know which way around it is on the surface. So we took a whole bunch of different directions of this particular molecule where we can compute the descriptor that corresponds to that configurations, and then we matched these two, like the experimental predictions, to the reference ones that we have. And there's like 500 different ones of these, and then we just, of that set, we found the best ones.
Yes, but what does that tell you? Does it tell you that your network output is reasonable? This I'm not sure, because you can just find, I mean, there's one matching, okay, but is it the one that you actually measured? You're not sure, right?
Yeah, I wouldn't say that's the conclusion would be that this is now the exact like configurations, but we get some list of likely configurations which like constrict the search space, and we see that the match is reasonable both by the descriptors and also like comparing the simulation AFM simulations to the experimental AFM images. So yeah, I think this does show that the output of the network is somehow reasonable.
Yeah, I'm not sure I fully agree with that. But so, for example, in this case, also what you could do is match the simulate AFM images with the experimental AFM images. You probably get a good idea what the orientation is, right?
That's a bit more difficult because in the experiment, how far you are actually from the sample is not easy to determine. So matching the simulation exactly is quite difficult, and also the simulation is not like, there's some effects in the experiment that are not like well accounted for in the simulation, so that, for example, in this case, there's some weird thing in the experiment in this case, which is not there in the simulations. And from the sort of expert point of view, we can like say that it's reasonable that the simulation doesn't have that kind of effect. But if you did some kind of very simple matching between the experimental and simulated images, then it might be very difficult to do in any kind of automated way.
Okay, yeah. I'm still not sure what you can conclude from these experiments, I have to say. Yeah. Anyways, okay. I'll have to think about it a bit more.
Do you have other questions, Daniel?
I do, but probably not. I won't want to keep everybody's time.
Well, you can just ask a couple more, maybe.
Let's see. Let me open what I had. Yeah. So. One question I do have. So, is there a reason why you chose to, let's say, ask the network to output, say, both the disks and the spheres and the height map at the same time, instead of just picking one or having separate networks outputting each thing separately?
Yeah. So, in my early experiments, I did have like individual networks for each one of these. But if you want to get all of them, then it's computationally more efficient if you just have one network which has some shared part. And also, in practice, I found that the model predictions were more robust when it did all of these at once. So it seems it has some kind of regularizing effect on the model.
Yeah, I could see that let's say some training signal for one could help the training of the other, for example, as well. But you could run into, let's say, scaling issues where, because you use mean square error, I guess,
Yeah.
some differences in one of the maps might be more penalized. Some errors in one of the maps might be more penalized compared to the other maps. For example,
yes.
you mentioned that for the atomic disk, you had to remove the ReLU because otherwise it wouldn't work. I think this could be related to that because it's a much, let's say, smaller training signal. In other words, it can just give a 0 image for the atomic disk, and then you're not penalizing it, the network, very much compared to doing a 0 for the height map, for example.
Yeah. And I think that is exactly the reason why it easily got stuck in that way. And for this reason, we also we add some like prefactor to the loss for the different components. So the other disk have like times 20 and height map is like times 0.1.
Fair enough. Okay. So you kind of normalize the output image.
Yeah. Though I think ideally maybe the loss function would be somehow dynamically normalized so that it would somehow, but yeah, I haven't looked into that too much.
Yeah. Because even normalize, it gets tricky, I think, because if you have a lot of, let's say, high molecules, then your height map suddenly becomes very, say, strong compared to the other ones. So it's a bit, everything gets a bit complicated, I think. So maybe just, you could maybe still have to combine network, but training maybe separately or something, it might, might work better as well. At least avoid these kind of getting stuck problems. Anyway.
Okay. Good. If you have no more questions, Daniel, then I would say let's thank Nico again. And now I would ask everybody to leave and only Daniel and Adam to stay, so that we can briefly discuss. Okay. Bye-bye, everybody.
See you.
Adam, have you sent Daniel the report template?
Yes.
Okay.
I think I did. Yeah.
Okay, good. Because I wasn't CC'd on that email. Okay, so then you have it,
Yeah.
Daniel, so you know what to fill out.
Yes. So how does that usually work? I mean, do I fill it out myself, or do we fill it out with the